Greetings, ladies and gents, and welcome back at Sir Mike Maths and Science Club. So, in the previous lesson, we looked at work done, and we said that work is done when a force causes movement. So, we say that work in this case is done when a force causes a movement. So, in this case, we did a lot of calculations using this equation for work, which says this is work done at work done, this is by force equals to in this case to the magnitude of the force multiplied by the magnitude of the displacement multiplied by the cosine of the angle between the direction of the displacement and the direction of the force in question. So we did a lot of calculations involving this formulae. Right, I think we actually did two. Right now, if you haven't watched that video, what I'm simply going to do is that I'm going to to put the link to that video in the comment section so that you can go back to that video and watch it first before you can continue with this one. Now, in this lesson, we'll just we'll be looking at energy. Right, we'll be looking at what energy is, what it does, and why it matters. But before we go into the definitions, I just want to to kind of reflect on this energy part before and relate it to to real life, so that we understand it a little bit better, so that it makes a little bit sense when we go into that. Now, most schools in South Africa, right? Most of you guys do sports, like on Tuesdays and on Wednesdays, and afterwards you would start walking. You would start walking, in this case, back home. Now, have you ever noticed that after walking that long walk from your school to your house, after the sports, right, immediately after you get home, it becomes impossible for you to do something like like lifting a heavy box? Like, your body just says no. Now, have you ever wondered why that's the case? Now, I know some parents would say it's because they would say that it's because you're lazy. When right, my mother would say that to me every time when I was a kid, when I'm too exhausted to do something. Now, that's not laziness. The fact that you are unable to get any work done is because you do not have enough energy in your body. So that's the reason, right? Because think about it. Why does a phone switch off and stop working if you do not charge it? Why doesn't a car start moving without fuel? And the answer to that is simple. It's because they do not have energy. But if you have energy, then you can have the ability to do work. So in physics, we define energy as the ability to do work. So if you have energy, then in this case you can do work. But if you do not, well, nothing happens. So we say that in this case, we say that energy is what makes things happen. Now, remember what we said about work. We said that in this case, work is done when a force causes, in this case, a movement. So now we can further say that energy is what allows that work to happen. So if there's no energy, nothing happens, nothing works, and nothing changes. Right. So in this case, if there is no energy, right, so that simply means that in this case, no work in this case possible. So there's no work possible. All right. Now, before we dive into the concept of grade 12, let's just take time to reflect on what we should know about, of course, about energy from the previous grades, right? From grade 10 and 11, so forth, and I think it's from grade 10 up to grade 11. Now, if we rewind back to grade 10, you learned of two types of energy. You learned of what is known as the kinetic energy. Right? So the types of energy. So you learned of what is known as the kinetic energy. which is the energy of motion. So this is the energy of motion. And we did a calculation on this. We said that in this case, to calculate the kinetic energy of an object at a certain point, we said that in this case ek, that's not E. So we say that in this case Ek is simply equal to a half multiplied by the mass of the object multiplied by this case by the speed of the object, but we square that speed there. So in this case M stands for the mass, and of course V stands for the speed of in this case of the object, right? In this case while it is moving. Right? So in this case we know that of course energy in this case kinetic energy, it is actually measured in joules. So in this case the first type of energy that we learned of was in this case the kinetic energy, which is the energy of motion. And the second energy that we learned about is actually the potential energy, potential energy, which is in this case the energy of position, the energy of vertical position there. And we said that in this case to calculate in this case the potential energy of an object, we said that in this case AP simply equal to the mass of the object multiplied by the gravitational acceleration value, which is 9.8, and you multiply that by the vertical height in this case of so we multiply that by the vertical height. Now suppose let's say we have an object that is in this case elevated, let's say 5 units, 5 meter right above the ground, above that horizontal surface there. So in this case this height would simply be that vertical height there. Alright, so let's say that's 3. So in this case that height there would simply be in this case this vertical height that we have there. So in this case H stands for the vertical height, and in this case G stands for in this case for the acceleration value, which is always 9.8 right meters per second squared. And we also learned that in this case when we combine these two, when you combine the kinetic energy of an object and its in the potential energy, we actually get what is known as the mechanical energy. So we get what is known as the mechanical energy, which we said to calculate us. So in this case the mechanical energy, we said that's actually equal to the product of the object's potential energy and in this case it's kinetic energy. And we say that in this case ME, right, which is the mechanical energy, we say that ME simply equal to the potential energy of the object, right, mgh, plus in this case the kinetic energy of the object at that particular point. So in this case this would be half multiplied by the mass multiplied by the speed, but we square that. Let me just add a page there so that we don't run out of space, right? And in this case but in grade 10 we actually also kind of expanded even further, stating that if we were to put this in an isolated system where in this case where no external forces exist, such as the kinetic frictional force, the kinetic friction, tension, air resistance, then in this case the mechanical energy of the object or of the system between any points would be in this case would be conserved, or it remains the same. So in this case we can say that in this case the mechanical energy of the object remains the same only in this case in an isolated system. So this is actually where the principle in this case of mechanical energy came from, which stated that in an isolated system the sum of the kinetic energy and the potential energy is conserved or remain the same. So in this case this mechanical energy, which says that the mechanical energy principle, which says mechanical energy before in this case or at a certain point would be equal to the mechanical energy in this case at another point. Suppose let's say we had in this case, let's say surface like that, let's say it is elevated, let's say 5 units there, it really doesn't matter, So in this case, if in this case in this system there is no frictional force, so that would simply mean that in this case let's say this point A and that's point B. So if we are in an isolated system where there is no frictional force, tension force, applied force, and so on and so forth, then we can say that in this case the mechanical energy of the object is conserved. So in this case, this is when, so in this case, if we were to expand this, then we would have in this case mgh, right, at point A, plus in this case half multiplied by the mass multiplied by the speed squared at point A. So this simply be equal, so this is simply supposed to be point B there. So in this case, simply be equal to the mechanical energy at in this case of the object at that point there, at point B. So we'd say that in this case mass multiplied by the gravitational value multiplied by the vertical height at point B, plus in this case the half multiplied by the mass multiplied by the velocity velocity of speed squared at point B. So in this case we would say that in this case if we are in an isolated system where there are no, in this case, external forces, then we would say that the mechanical energy at one point would simply be equal to the mechanical energy in this case of the object at in this case at that other point. But in this case, remember, this is only applicable in an isolated system. Let me just write that down there. Isolated system where there are no external forces, such as this case, such as frictional force, right, such as also in this case if there is no, in this case, applied force, and in this case if there is no, let's say in this case, the tension force. So in this case, if our system does not have frictional force and it does not have also in this case it does not have the applied force or tension force, then we can say that in this case our system is isolated. Then in this case we can be able to use this principle here, which is the mechanical energy principle, which states that in this case in an isolated system the sum of the potential energy and in this case the kinetic energy of an object is conserved at any given point, right? And we did a lot of calculations based on this principle. So this was actually a big idea of what we it was actually a big idea, right, in grade 10, and we did a lot of calculations based on this on that principle there. Now what I've done is that I've kind of prepared questions down there, which is actually questions from those from the previous grades. So what we're going to do, we're simply going to to apply in this case what we know from grade 10, right, in answering this this question here. So they say that in this case, so they say for question 1, they say that in this case an object of mass 0.2 kg is released from rest at point A and moves along the frictionless section, which is AC, of a curved track. Now you have to forgive my English sometimes. This sometimes this English kind of defeat me. So they say that along section CD it experiences. Now what you must just note is that they said that in this case an object of mass 2 kg is released from rest at point A and moves along the frictionless section AC, which is this section that we have here. So they're saying that that's actually a frictionless section there, so we do not have friction there. In this case, they also say that along section CD, this section, they say that it experiences a friction of 0.45 in this case Newton, and stops at point D. So they say, so in this case between point C and D, on that point we actually have friction, right, acting on the object. But in this case between point A and C, we do not have a frictional force acting on the object there. So they say that the vertical height of point A above X, right, on the ground is 8 meters, is shown below. So they say that in this case calculate the gravitational potential energy of the object at point A just before it is released. So in this case we know that of course to calculate in this case the potential energy in this case of an object, we say that in this case we say that EP, which is potential energy, is simply equal to the mass multiplied by the gravitational value multiplied by the perpendicular height. But remember, they want the potential energy of the object right at that point A. So in this case, it will be at point A. So we know that, of course, the mass, that's 0.2, right? And in this case, G, remember we said that's the gravitational acceleration value, which is always 9.8. Right? We multiply that by the vertical height, right? So that will simply be, in this case, 0. So that's actually 8. That's 8 there. And if you were to put all of this into your calculator, what you're simply going to get is actually 15.68 joules. So that would be, in this case, the potential energy of the object at point A. So in this case, the SI units for potential energy is simply joules. So in this case, for 1.2, they say that use the principle of conservation of mechanical energy to calculate the speed of the object at point C. So in this case, remember they said that this object was in this case released. All right, in this case, they said that it was released from rest, meaning that the speed of this object at that point A is simply 0. Right, so in this case, now what they are simply asking us is to calculate its speed when it gets to that point C. So what we are simply going to do, so they said that it used the principle of conservation of mechanical energy to calculate the speed of the object at point C. So in this case, what you must just note is that in this case, as this object is traveling between these points, right, in this case, it is not experiencing any frictional force. So we notice that in this case, there is no applied force. There's no force that is being applied on that object. There is no frictional force and there's no tension. So that simply means that in this case, we are in an isolated system. So we can actually use that mechanical energy there, which says in this case, the mechanical energy right at point A would simply be equal to the mechanical energy of the object at point C, at that point there. So in this case, we can expand this to being, remember that mechanical energy, we said that's the potential energy of the object, all right, at point A, plus, in this case, it's kinetic energy at point A, but remember that's V squared. So do not forget to square that speed there. So it's simply be equal to the mechanical energy of the object at point C as well. So this simply be mgh at point C plus its speed, its kinetic energy, which would be half mass multiplied by the speed squared. So in this case, what we can do would be, in this case, to substitute in this case our values. So in this case, the mass, that's actually 0.2, right? In this case, the gravitational acceleration, that's 9.8. In this case, our height at that point there, simply 8. So put that in 8 there, right? Plus a half multiplied by the mass, which is 0.2. Write it down. Remember that. So in this case, remember that, of course, they say that this object was actually released from rest, right? So in this case, meaning that the velocity at point A is simply 0. So we square that. So it's simply be equal to the mass, which is 0.2. But remember that at point C, this object is actually on the ground. So that means that in this case, at that point C, that object is not elevated any units above the ground. It is actually on the ground. So that simply means that in this case, its vertical height at that point C is simply 0. Why? Because it is actually on the ground there. So it simply become 0.2 multiplied by 9.8 multiplied by 0 there. Right? You could have just put, a 0 there, but yeah. So in this case, simply be plus a half multiplied by the mass, which is 0.2, multiply that by speed, which is, remember that we're trying to calculate the speed of that object at point C. So it's simply be, we're simply going to leave that as VC squared there. So in this case, if you put this into your calculator, you'll notice that it is actually the same as that. So in this case, you're simply going to get 15.68. Right. So in this case, what you can do there is to say, so in this case, simply be equal. So in this case, actually, these two simply going to give us a bunch of zeros. So in this case, just gonna drop this. So you're gonna drop those two. Why? Because they're actually going to give us zeros there. So simply becomes, so in this case, a half multiplied by 0.2, we're actually going to get 0.1. So this will be 0.1 multiplied by the speed at point C squared. So what we are going to do would be to divide by in this case by 0.1 on both sides. So if you divide by the 15.68 by 0.1, what you're actually going to get is actually 156.8. So it's simply be equal to v, to velocity, to speed at point c squared. Now in this case, to get the speed, remember that this is simply v squared. Right? So in this case, what you're simply going to do there would be to take the square root on both sides. But since they are just asking for the speed, we won't actually just concern ourselves about about the direction. So in this case, what we are simply going to have would be v at point c being equal to, in this case, 12.52, in this case, meters per second. Right, so in this case, remember to put the SI units. Right, you must put that every time, because if you do not put the SI units there, it won't make any sense. Right, so in this case, now my issue with this, so in this case, this simply be, in this case, so this will be the speed of the object at point C. But if you noticed, they said that along section CD, it experiences a frictional force. Now, my issue with this principle, the mechanical energy formula, which says M mechanical energy at point A, all right, equal to, in this case, the mechanical energy at point, let's say, B. Now, my issue with this principle is that it only works in an isolated system where there are no external forces. That's where it works, right? So in this case, this mechanical energy formula, right? This mechanical energy formula, it only works in an isolated system where there are no external forces, or where there are no what we call as the non-conservative forces. Now, let me just let me just hang on a bit. Right? Feels like we are going a little bit fast, right? What are non-conservative forces to begin with? Because it feels like I just dropped a bomb there. Now, non-conservative forces, all right? So in this case, because I feel like I just dropped that word there. So in this case, non-conservative, conservative forces. So we say that in this case, non-conservative forces are forces whose work done in moving an object between 2 points depends on the path taken. Right, so if you look at the frictional force, so in this case, suppose let's say I had an object, right, that in this case I'm pushing in that direction there, right? So in this case, remember that if I'm so let's say that I'm pulling that object in that direction. So in this case, if this is a rough surface, so that simply means, of course, that we have a frictional force. So if you look at the frictional force, so in this case, the direction of the frictional force, it actually depends on which direction my object is actually traveling. So in this case, if my object is traveling in that direction, so let's say that's the force applied there. So that simply means that in this case, the direction of the frictional force would simply be, in this case, to the left. So it simply be Fk. But if I were to change this and pull this object in the other direction, which would be to the left. Now I want you to notice the direction of that frictional force. So in this case, if I change, in this case, my applied force, in this case, and apply it to the left, I pull that object to the left, my applied force there. So you notice that in this case, the frictional force would actually change direction. So in this case, it would be acting to the left. So it simply be, in this case, my frictional force. So in this case, if my object is traveling to the right, then the frictional force would be to the left. But if my object is moving to the left, the frictional force would be to the right. So the direction of the frictional force would simply be to the right. So in this case, so since the direction of the frictional force in this case depends on which path that I take in this case, on which path in this case I'm traveling. So due to this effect, that in this case for the frictional force, so that's actually the frictional force. So for the frictional force, so that's actually Fk. So in this case, due to this effect, that in this case the direction of the frictional force depends on which path I take. They actually called it a non-conservative force. So in this case, a non-conservative force is a force that actually is a force whose work done in moving an object between 2 points depends on the path taken. So in this case, you notice that in this case, if I'm moving to the right, my frictional force would be to the left. So if I'm moving to the left, my frictional force would simply be, in this case, to the right. So in this case, the direction of the frictional force depends on which direction I'm actually moving. So in this case, due to this effect, that in this case for the frictional force to take an effect, for it to decide its direction, so it actually depends on which direction that I'm actually moving, right? On which direction I'm actually moving, in this case my object. So in this case, due to this effect, they actually called it a non-conservative force. So in this case, other examples of non-conservative force, let me just write there, non-conservative. That's actually not right there, so let me just rewrite that again. So that's non-conservative force. So remember, we said that in this case, non-conservative forces are forces whose work done in moving an object between 2 points depends on the path taken. So you notice that in this case, the direction of the frictional of the frictional force actually depends on the path taken. So in this case, the frictional force is actually one of the non-conservative force. So the other one, so in this case, the first one, non-conservative force, is actually the frictional force. Let me just rewrite that. So that's frictional force. So you must just keep that in mind. So in this case, frictional force is a non-conservative force. The other one is simply tension force. The other one is actually, in this case, also the applied force, and also in this case, the air resistance. So in this case, these are the examples of so let's say air. I think that's not air. So that's air. I believe that's it is air resistance. So in this case, these four are simply the examples of, in this case, of non-conservative forces. So in this case, we say that these three are actually non-conservative forces. You can in this case, non-conservative forces are simply external forces, right? You can treat them so you can call them that way, but in this case, we just prefer to call them in this case non-conservative force. So in this case, non-conservative forces are forces whose work done in moving an object between 2 points depends on the path taken. So you must know that definition. They love to ask it in the exams. So in this case, we say that the examples are frictional force, tension force, applied force, and air resistance. But now, if you look at the force of gravity now, the force of gravity doesn't obey anyone's rules. Gravity is crazy, right? If we look at the work done, or if we look at the direction of the force of gravity. Now, suppose, let's say I had an object. All right, let me see if let me just put another page so that we have more space again. Seems like I'm running out of space a lot. So in this case, if we look at the force of gravity, right? Now, if I'm pulling this object, I want you to check, in this case, the direction of the force of gravity. So if I'm pulling that object to the right, you would notice that in this case, the direction of the gravitational force would simply be downwards. So in this case, the gravitational force would be downwards. So even if I'm moving my object in that direction, in this direction here, so this case is in this case it would be, in this case, my applied force. So if I choose to apply my force in that direction to the left, my force of gravity would still be downwards still. And even, let's say, I'm moving this object up an incline. Let me just draw an incline there. Let me just draw it there so that it makes sense. So in this case, if we have, in this case, the force of gravity there, you would notice that in this case, the force of gravity would still be, in this case, it would still be to, in this case, downwards. So in this case, the force of gravity would still be downwards. So in this case, no matter where my object is going, whether being to the left, right, whether being to the left, right, up or down, or even in this case, up an incline. So in this case, the direction of the gravitational force is actually always downwards. So as a matter of fact, the work done by the force of gravity would also be, in this case, downwards, no matter which path. In this case, no matter which path I take. So in this case, due to this effect, that in this case, the work done by the force of gravity, or the direction of the force, in this case, let me just put it in terms of in its formality. So in this case, due to this effect, that in this case, the work done, in this case, by the force of gravity in moving an object between 2 points does not depend on the path taken. So in this case, they actually called it a conservative force. So in this case, they actually called in this case Fg, right? Fg, in this case a conservative force. All right, let me just so in this case Fj is actually in this case a conservative force. So in this case, so a conservative force is actually a force whose work done in moving an object between 2 points does not depend on the path taken. So in this case, the examples of conservative force simply in this case includes in this case the gravitational force. In this case, simply be in this case the gravitational gravity. Let me just say gravity simply means that let me just write in gravitational force, gravitational force. So in this case, due to this effect that in this case gravitational force, not forces, so due to this effect that in this case the direction of the gravitational force does not depend on the path taken, so they actually called it a non-conservative force. So in this case, a formal definition for a conservative force, in this case, your gravity is a conservative force. I think I kind of said it the other way around. So due to this effect that in this case the direction of the gravitational force does not in this case depend on which path in this case I take. So in this case, they called it in this case a conservative force. So in this case, a conservative force, by formal definition, you must know this definition. So so a conservative force is a force in this case whose work done in moving an object between 2 points depends on the path does not depend on the path taken. And we say that in this case an example of conservative force is simply in this case the gravitational force. In grade 12 it says this is the only conservative force that we have. I don't know in the university, but in this case for grade 12 this is the only in this case this is the only conservative force that we have. Now going back to what we said, remember we said that in this case the mechanical energy formula, which says in this case ME at point A simply be equal to ME at point B. Right, so this is actually the mechanical energy. Right, remember that in this case, now going back to what I said again, remember we said that this formula, it only works in an isolated system where there are no non-conservative forces, right? So where there are no external forces. Now, the question is, what happens if we have these non-conservative forces? What happens then? Now, this is actually where the grade 12 work comes into play, because we have two new energy principles which actually work when we have non-conservative forces on our system, or when we have in this case external forces, which is actually the non-conservative force formula, which says that in this case the work done, so in this case which says in this case the work done by the non-conservative force, right, is actually equal to the product in this case of the, so in this case the non-conservative force is actually the work done by the non-conservative force is simply equal to, in this case, to the change of the object's kinetic energy, right, plus the change of the object's potential energy. So in this case, so this is the principle that we use when we have in this case non-conservative forces on our system, so when we are not in an isolated system. So this is one of the formulas that we have. So we remember we said there are two. We can introduce the other one that we have. Remember that in this case we said in this case the non-conservative forces that we actually have in this case the applied force, frictional force, tension force, and so on and so forth. So in this case, when you say that in this case this W and C is simply the work done by all the non-conservative forces that will be there in this case on your system. So in this case, I would say that in this case, so this part would simply be in this case W, the work done by in this case by the applied force, plus work done by Fk, plus work done by in this case by tension force, plus in this case also work done by air resistance. But let's just neglect that air resistance. So in this case work done, so in this case that W and C is simply the work done by the non-conservative force. So if you only have one non-conservative force in your system, so you simply just neglect the other ones, just leave that one. So you just in this case you'll be left with the work done, let's say, by the frictional force. So if you only have frictional force on our system, so in this case the work done by the non-conservative force would simply be, in this case, that W. So it would simply be left with that, which just in this case WFK. So in this case, so it simply be equal. Now if we of course kind of follow this, so we say that in this case the work done by the non-conservative force simply be equal to, in this case, to the change of the object's kinetic energy plus the change of the object's kinetic energy of the potential energy. So simply be in this case, so simply be in this case half multiplied by the mass multiplied by the speed squared at point A. In this case, let's say we have 2 points. In this case, let's say we have something like that at that point there, that point there. Let's say we have, in this case, friction on that point. So we say that in this case, work done by the non-conservative force that we have on our system equals to the change that object is change in kinetic energy, right? So this will be so in this case simply be final. So simply be B. Let me just erase this. Simply be, in this case, the final at point B. This case minus a half mv squared at point C at point A. So in this case it is final minus initial, simply be plus, go to that one. So in this case simply be, in this case, the potential energy of the object at point B minus, in this case, the potential energy of the object at point A there. Right, now the beauty about this formula is that it works when we have non-conservative forces, which are the external forces, but it also works when we do not have the non-conservative forces, as it actually automatically converts itself into the mechanical energy formula, right? So in this case, so if we do not have, in this case, the non-conservative forces on our system, then we can just simply put in this case a 0 there. So if we do not in this case have non-conservative force, simply just put a 0 there. But in this case, what we prefer in this case to do is that when we do not have non-conservative force on our system, we can just simply use in this case the mechanical energy. So in this case, what you must just note is that this formula works in an isolated system. Right. So in this case, now again, one thing that I must mention is that this formula, right, it works in this case in a curved surface, like in a surface like that. Right. So it works in a curved surface, but it also works actually on a vertical surface, so on a surface like that, on a vertical surface, but it also works in this case on an inclined surface like that. All right, it also works, and it actually also works in this case on a horizontal surface. So in this case, it actually works on both frictionless surface and in this case one which has, in this case, friction. So you must just keep that in mind. So in this case, this formula works in this case on a curved surface. It also works in this case in a vertical. Surface, if you want to put it that way, and also in this case on an inclined surface. So you must just keep that in mind. Surface. All right. So in this case, that's where this formula works. Now, again, going back to what I said at the beginning. Now, remember I said we have two new energy principles there, right? To our equation, which works when we have, in this case, the external forces or non-conservative force on our system. And we say that in this case, this is the first. And the second one, let me just add another page again. Seems like I'm running out of space every time. And the second one that we actually have, which is the most important one, is actually the Work-Energy Theorem, which says that in this case, the work done on an object by a net force is equal to the change in the object's kinetic energy. Right. So in this case, that's the Work-Energy Theorem definition. So the Work-Energy Theorem definition says, in this case, that the work done on an object by a net force is equal to the change in the object's kinetic energy. So in this case, we say that in this case, work done by the net force, right, by all the forces that are acting on our object, including the gravitational force. So in this case, so we say that work done by the net force is simply equal to, in this case, to the object's change in kinetic energy. Right, so in this case, this would simply be the work done by all the forces in this case on our system. So in this case, the formal definition for the work energy theorem, so in this case it's actually the work in this case energy theorem, right? So which says that in this case the work done, right, by the net force on the object is equal to the object's change, or to the change in the object's kinetic energy. Or you can say that the net work done on an object by or you can say that the net work done on an object is equal to the change of the object's kinetic energy. All right, now one thing that I must say, right, I must warn you about this formula, right, is that this formula, now the issue with this formula is that in grade 12 is that it doesn't work well on curved surface, like on a surface like that. So in this case, if we have like a curved surface, we do not use this formula, right? You must just keep that in mind. So in this case, it only works well in this case on horizontal surface. So in this case on horizontal surface. In this case, it also works in this case on inclined surface like that, and it also works in this case on vertical surface. So in this case, you must just keep this in mind. So in this case, this formula, it does not work well in this case on a curved surface. It works, but it does, I don't like the way it works. So you must just keep that in mind. So in this case, if we are dealing with the object in this case on a curved surface, so what we just do is that we scratch this one out. So in this case, what you do is that you use the one principle that best fits the situation, or that best fits the condition of your system. So in this case, what you do is that if they say that in this case use energy principle to calculate a certain whatever, so what you do is that list all your energy principles, and in this case you just eliminate them one by one based on the conditions that you have. So in this case, what we are simply going to do, let me just show you what I mean, right, by looking at the examples that we have down here. All right, so in this case, remember, these are the energy principles that we now know, right? So in this case, the first one is the mechanical energy, but remember, this works in an isolated system. But in this case, we also have in this case the one that doesn't work, that does work in this case when we have external forces, which are of course the which works when we have in this case non-conservative force, right? And we also have in this case the that network done, energy theorem, that work energy theorem there, right? But remember, this one does not work when we have a curved surface like this one that we have here, so we don't use that one. So in this case, if we look at this question, which was written in November 2019, right, they say that in an object, we're simply going to do one question, unfortunately, so that we can just I don't want to make this a very long video, even though I feel like it's the longest video I've ever made so far. So in this case, question 5, they say that an object of mass 1.8 kg slides down on a rough curved track and passes point A, which is 1.5 meter above the ground, at a speed of 0.95 meters per second squared. 0.95 meters per second. So they say that the object reaches point B at the bottom of the track is at a speed of 4 meters per second. We can see that. And in this case, they say that for 5.1, define the term conservative force. So we know that definition there. We know that in this case, a conservative force is a force. In this case, it's a force. So a non-conservative force is a force whose work done in moving an object between 2 points does not depend on the path taken. So you must just keep that in mind. And in this case, for 5.2, they say that name the conservative force acting on the object. Remember that we said that conservative forces that we have is simply, in this case, the gravitational force. Gravitational force. So this is the only conservative force that we have. So this is the gravitational force. All right. And in this case, for 5.3, they say that is the mechanical energy as the object slides from point A to B. So is the mechanical energy conserved as the object slides from point A to B? They say that choose from yes or no, give an answer for your reason. And we know that, of course, this is actually a no. So in this case, the mechanical energy in this case is not conserved. Why? Because in this case, if you look, they say that in this case, this is a rough curved surface, meaning that in this case, we have in this case we have we have frictional force there. So in this case we can't say in this case the mechanical energy is conserved. Why? Because in this case we have external force, or what we rather call as the non-conservative force. So they say that give a reason for your answer, because in this case we have non-conservative force, conservative forces. We have a non-conservative force, so that would be a reason there. So in this case it cannot be conserved. Why? Because in this case we have non-conservative force on our system. So in this case for 5.4 they said that calculate the gravitational potential energy of the object when it was at point A. So in this case we know that of course to calculate the gravitational potential energy, we said that EP simply equal to the mass multiplied by the gravitational value multiplied by the height, the vertical height. So it simply be equal to the mass, which is 1.8, multiply that by 9.8 multiplied by the vertical height, which they gave to be in this case 1.5. So in this case, so that's 1.5. So if we put that into our calculator, what we are simply going to get is simply an answer of 26.46 there joules if we rounded that off. So in this case for 5.5 they say that just enlarge this a bit. So they say that in this case for 5.5 they say that you use energy principles, using energy principle calculate the work done by friction on the object as it slides from A to B. Now remember we said that this is a rough track, so meaning that we have frictional force there, but remember frictional force is a non-conservative force. So in this case, so what we do in this case to calculate that so they say that calculate in this case the work done by the frictional force. So in this case what we need to do, now remember that they said that using energy principle. Now remember that these are the energy principles that we have at our disposal. So in this case we cannot use this one. Why? Because in this case we say that this doesn't work well on a curved surface. So in this case the only principle that would actually work would be that one there. So in this case what we are simply going to do would be to say in this case work done by, in this case so we say that work done by the non-conservative force simply be equal to the object's change in kinetic energy plus its change in potential in this case in EP. It's potential energy. Now in this case what you need to ask yourself, so in this case this will be the work done by the non-conservative force. So what you need to ask yourself is that how many conservative force that do we have here? So you notice that in this case frictional force is the only conservative force that we have there. So in this case this simply be in this case the work done by, in this case by what, by Fk. So in this case this, so if we only have in this case frictional force on our system, so in this case the work done by the non-conservative force would simply be work done by the frictional force there. So simply be equal to, so this would be half, right, multiplied by the mass multiplied by the speed squared at point B minus, in this case half multiplied by the mass multiplied by the speed squared at point A, initial final minus initial, plus in this case mgh at point B, right, minus in this case mgh at point at that point, which is point at point B there. So in this case what you simply do there would be to say half multiplied by, in this case the mass of the object, which they gave us to be what was that value there? So in this case the mass is actually 1.8 multiplied by the speed at point B, which is actually 4, but we square that, right? So in this case what we do would be to say, so in this case that's squared minus half multiplied by the mass, which is 1.8 multiplied that by the speed of the object at point A, which is 0.95, and we square that. You always remember to square, right? So in this case simply be the mass, which is 1.8 multiplied by, in this case by the gravitational value, which is 9.8, multiply that by, in this case by the vertical height at point B. So we know that at point B that object is actually on the ground. So in this case simply be the vertical height will simply be 0. So simply be minus. So in this case will be minus, in this case the mass, we're going at that part now. So in this case simply be mass 1.8 multiplied by the gravitational acceleration value multiplied by the vertical height, when that object is so I think actually I kind of twisted it around. So in this case simply so supposed to be final minus initial there, simply be A. My apology there. Let me just erase this nicely so that it's not a mess. So it's simply be, so this is A, so it's final minus initial, so simply be multiplied by, in this case by 1.5 there. Now if you put all of this into your calculator, what you're simply going to get, now remember that simply give us a 0 there. So if you put this all right into your calculator, what you're simply going to get would be in this case work done by the kinetic friction to be, in this case, to be negative 12.87 joules if you round that off there. So in this case this will simply be your 5.5. So in this case how you know which principle to use when they say that use the energy principles. So in this case what you simply do is what I did there. So in this case you notice that these are the energy principles that we have at our disposal. So in this case this was unable to work. Why? Because in this case we are not in an isolated system. But in this case this also cannot work. Why? Because in this case we are actually working on a curved surface, right? So in this case the only one that was left there would be that one. So in this case we use the principle that actually that meets the requirements of our system. So if we look at 5.6, they said that surface BC, where is BC? I can't find BC there. All right, they said that BC in the diagram above is frictionless. I suppose there was maybe another check there. So let's say there was a point C there, which I think I kind of removed it out. I don't know why I did that. He said that surface BC in the diagram above is frictionless. What is the value of the net work done on the object as it slides between point B to C? So in this case, remember they say that in this case we have a section there which is BC, but in this case they say that in this case there is no friction acting on that object. So in this case, if there's no friction, in this case the only force that will be acting on that object is simply the gravitational force. Right, so in this case we know that of course the work done by the gravitational force perpendicularly to our surface. Right now we are actually on a horizontal surface there. So in this case we know that the work done by FG is simply 0. So in this case we can say that in this case work done by F net, right, is actually equal to 0. So in this case the net work done on that object as it was sliding from B to C is simply 0. Why? Because in this case we do not have forces acting in this case on that object except the force of gravity and in this case the normal force, which we know that of course the work done by those two, in this case the work done by the gravitational force perpendicular to our surface is simply 0, and also in this case that the normal force. So this simply be in this case it for this video. Right, I apologize for making it a long video, ladies and gentlemen, just that there was a lot to uncover there, right? But otherwise, ladies and gentlemen, this is it for today, right? If you enjoyed this video, be sure to leave a thumbs up, right? If of course you have any questions, be sure to ask in the comment section, or if you have any topic that you would like me to cover next, be sure to just suggest that in the comment section, whether being in maths, physics. All right, you can always just suggest that. Now what I'm going to do is that they actually practice questions that I've made down here. So in this case I'm actually going to do more videos. I think there are 4 videos that is actually dedicated to what we did in this video, right? So be sure to subscribe, or in this case, and also turn that notification bell so that in this case when the next video comes up you'll be notified. But otherwise, ladies and gentlemen, as the story always ends, this is Sir Mike signing out. Sharp.